So we will continue. Okay, so so we were actually discussing the case two. Okay, for the density distribution for the normal density. Okay, with respect to the decision boundaries, and then we have seen maybe the different the possibilities of hyperplanes actually in various maybe dimensions like. One dimension, two dimension, three dimension, and maybe that can be extended to multi dimensions also. So we have seen maybe this particular case, and this is actually another case. Okay, suppose we are having a I mean a single dimension. Okay, data. So where we have actually maybe say two regions. Or so for example, suppose we are having actually maybe there's a two class problem w1 and w2. Okay, w1 and w2, and so in this case we can see that this region corresponds to, that means in this region we can say that the probability of w1, okay, is actually larger. Okay, and correspondingly probability of x given wi is actually okay larger in that case. And similarly maybe but in this particular region we are having maybe so the other class is actually having the like more likelihood. And similarly we are having this is for, again for the first class. So we can say that that regions are actually non simply connected. Okay, so r1 is actually up to here. Again this region is actually say r1. Okay, so that means so the problem is actually having due to unequal variance, because if you look into this variance of these distributions, they are actually different. So that is actually the case two that we were discussing. We are having maybe say maybe different say variances maybe. Okay, with respect to maybe the I mean the features. Okay, but they are having with respect to the classes. Okay, they are having, but there can be situations like this also. Okay, we are having okay non simply connected decision regions. So when we come to case three, so that means we are having an arbitrary maybe say sigma. So that means it can be different for I mean the uh, can be different for so that means it can be different for the each of the categories or classes. Okay, so then we can actually maybe only remove this particular term. Okay, and then we have actually maybe the quadratic discriminant as we have seen yesterday. Okay, and it's a corresponding maybe some terms that we actually group together. Okay, so in order to have maybe these three terms. So that is a so here we can see that we are having x transpose into x. Okay, so that means we are having a maybe quadratic term comes. Okay, so that is it is not a linear discriminant. So in that cases we have seen that the decision boundary, okay, is generally called a hyperquadrics. Okay, so again the setting is actually j of x is equal to jj of x, but this can be maybe simple hyperplanes. It can be, or can be pairs of hyperplanes, or can be hyperspheres, okay, hyperellipsoids, paraboloids, etc., etc. So that is actually maybe the complex case. Okay, so that means so this is actually maybe one case we are having actually say maybe two hyperplanes. Okay, so deciding. Okay, so you can see that distribution maybe here also. Okay, and similarly this is again a pair of hyperplanes but in a different maybe ways. So you can see that so here it belongs to one region, here it belongs to another region. So there are a lot of complicated maybe possibilities can come. And this is maybe again a not a straight line. Okay, but it of this kind, and this can be an ellipsoid. Okay, it can be spherical. So all these possibilities are actually there. So the point is actually okay, maybe this is actually a non-simply connected region. So okay, maybe this region corresponds to one region, and this region corresponds to okay another region. So all this any possible maybe way of maybe or say any complex decision boundary we can actually expect it. Okay, when it comes to maybe higher dimensions. So that is a arbitrary Gaussian distributions. Okay, so that are that leads actually to base decision boundaries that are generally hyperquadrics. So that is actually the important interesting point. Okay, so and so that this is actually about maybe in 2 dimensions. So when it comes to 3 dimension, again the analysis and the concept everything remains same, but you can see that when the data is actually in 3 dimension, maybe our decision boundaries are going to be maybe in 2 dimensions. So that means we are having a plane as a hyperplane. Okay, hyperplane will be a plane. Okay, earlier it was maybe a straight line or a curve on a 2 dimensional plane. But when it comes to 3 dimensional maybe feature space, the hyperplanes are going to be in 2 dimensions. So that means you can see that it's a parallel planes. Okay, maybe this crossing one. Okay, maybe a curved one. So all these are really maybe it is a very difficult to imagine maybe okay, how this is going to happen. Maybe that depends on okay the complexity. Okay, maybe how the data is actually distributed. Okay, because here maybe the distribution of data. Okay, and here all in this analysis we assume that the Gaussian distribution is a data, but this whatever points that we discuss here is exactly applicable to maybe other distributions. Okay, suppose the data is actually distributed maybe it's a Poisson distribution, binomial distribution, or any complex other say distributions. So in that case also these are applicable, but maybe the decision boundaries all this we actually discuss are going to maybe change and maybe more complex. So that is actually the maybe one thing that we have to note. Okay, and these are again some of the other cases. Okay, so anyway, so just to give an maybe to get an idea about how complex these maybe decision boundaries can be, these figures are actually included. Okay, so that is a case, and this is a very interesting case. So for example, suppose we are having a 4-class problem. Okay, so that means suppose we are having a 4 normal distributions. Okay, so that define actually maybe the 4 maybe classes. Okay, so that is 4-class problem is going to be, it need not be a very complex problem, because it can happen very common in maybe in our say real life situations. Okay, but we can see that whenever that is a case, the decision boundary is actually very complex. So for example, if you consider this one, so the decision boundaries of maybe this kind. Okay, so and maybe this kind. Okay, so all these are actually very complicated one. So okay, so because that is a shape of the decision boundary, and maybe we know that it's a R1, R2, R3, and say R4 regions. So it's a very complicated maybe when we consider actually even a 4 case. Okay, possibilities. Okay, so all these depends on maybe how the covariance matrix actually varies. Okay, because each of these features having different maybe variances, and maybe the covariances are actually arbitrary. Okay, so that actually leads to complex decision boundaries. So that is a point we have always keep in mind. So maybe finding out such a maybe a decision boundary, okay, of maybe say this kind. Okay, maybe say for example something like this one. So all these are actually of maybe very difficult. Okay, so okay, so that is actually the case. So now so that is about actually generally about so maybe the I mean the 3 different cases and other things. Okay, with respect to so normal density. So we will not be discussing other maybe distributions, because the same the principles or the concept that we have actually discussed is actually applicable. Okay, so that is the case. And now we will go to okay maybe another. Okay, suppose just an example. Okay, how this can be we can apply maybe the how we can find out a decision boundary actually for a given data set. Okay, so now that is actually really interesting. So the point is that suppose we know that usually we will have a data. Okay, maybe assume that if the data is actually given in the form of a say tabular data, okay, where you have maybe say x1, x2, x3, etc., and we have at the class level. Okay, so x1, x2, x3, etc., with the class level. So the thing is that we know we need to, okay, and similarly assume that we have a few of them w1, few of two say w2, and say few of them say w3. Okay, it need not be in a continuous way arranged, but maybe for the time being, let us assume that all the w1 are actually grouped, okay, at the beginning, and then followed by w2, and then followed by w3. It need not be like this a data set. Okay, yeah, can be an overlap. Okay, so anyway, so the important point is you consider all the w1, okay, tuples, okay, and then we have to find out what is maybe mu1, okay, and maybe say sigma 1, and similarly for w2 also we have to consider mu2, okay, and then maybe say sigma 2, etc., so like that. That means we have to find out the mean vector, okay, and then maybe the maybe the covariance matrix in each case. So that is one thing that we have to find out. Okay, and so there are techniques actually. Suppose we know that the normal distribution that we have discussed is actually entirely defined by these terms. Okay, so that is the either maybe the mean vector and the variance or the covariance matrix. So that depends on whether it's an univariate or a multivariate problem. Okay, so now assume that we are having a given data set. So suppose something like this one. So these 4 points, black points, actually belongs to say, okay, maybe W1, and this red point say belongs to W2. Okay, so from a given data, we can easily find out maybe what is the mu1 and maybe for mu2. So here we know that so there are actually say two-dimensional data. We have x1 and x2. Okay, x1 and x2. So it's a two-dimensional data. So that means that we know that this is going to be the mean vector is going to be maybe, okay. So the mu vector is going to be maybe what is mu1 and maybe for mu2. Okay, so that is you can calculate from this given data, and similarly we can calculate the covariance matrix also. So it is going to be a 2 by 2 matrix. Okay, so that also we can calculate it. Okay, and once we calculate it, maybe mu vector, sigma vector. So once you find out maybe the covariance matrix, you can calculate what is our determinant. Okay, and maybe sigma inverse. All these we can actually calculate using the matrix. Maybe say operations. Okay, so if that is the case, okay, then so we are not going to the solutions. Okay, by maybe you can try. Okay, so for example, for that problem, suppose assume that mu1 is actually, okay, so mu1 is actually 3 6. Okay, then sigma 1, that is our covariance matrix for the first one is actually this one, and the mu2, okay, maybe, and say sigma 2. Okay, so suppose we found out these, okay, using the formula that we have discussed, and then accordingly we can actually find out the decision boundary. So that's a decision boundary. We know that that is a g of x function. Okay, that we have actually discussed in various cases. Okay, and then we can substitute this mu value, sigma value, okay, mu2, okay, and etc., so that you will get a maybe an equation of this kind, maybe in this case. Okay, so here, so if we look into this particular equation, okay, so if we look into this equation, we know that the decision boundary is actually the maybe the equation for a parabola. Okay, because it's an x1 square. Okay, so x1, and so that is x2 is equal to, okay, this is going to be the equation. Okay, so that way we can actually find out the decision boundary from the given data. Okay, and then we can look at maybe this plot also. Okay, and so there are different cases. Okay, whether it's a the prior probabilities are actually same for both okay, w1, w2. Okay, whether that is assumption or if it is a different and then by looking into the maybe the distribution of these points. Okay, so you can see that maybe say along maybe the x2 direction. So that means along the y direction, maybe. So the what is the difference between, okay, this point and this point, and similarly this point and this, whether that is same. Okay, or along the x1 direction. So that means along the horizontal direction here, whether that maybe the difference between these 2 points and maybe these 2 points. So we can see that there is a skewing of this actually along of this probability distribution of W1 and W2. When you consider, we can see that there's a skewing happens with respect to W1 case, because you can see that it is actually so very small actually the difference between these 2 points compared to these 2 points. So there can be impact on maybe so where the decision boundary will be passing through. So because we know that so there is an x0 we have calculated, that is x0 is actually the point through which maybe the decision boundary passes through. So we know that that is going to be this particular point. So that way we can actually look at the values and maybe have a maybe analysis, and that will give a more maybe information about maybe the underlying distributions. So this is a very simple example that we can actually maybe through which we'll get an idea about how we can find out a decision boundary for a given data. So we have to find out the parameters that are required in the decision boundary equation that we have already discussed from the given data, and then we have to see what is going to happen with the prior probabilities and what are the other information that is required. So that is actually the case, and so this is also we have just seen maybe since our cases. So that is about that particular section, and now we will actually go to the last session of this particular discussion. So here what we are going to discuss is this is so far actually we have discussed the so far we have actually discussed the I mean the continuous features. But we have initially we started the discussion with the discrete features, and then we switched over to continuous features. So whatever we discuss actually, whether for discrete or continuous, they are going to be applicable to both. But the only thing is maybe the notations in some textbooks will be varying, maybe maybe the equations, maybe how the probability it's actually defined for discrete and continuous cases can differ. But the main concept or the fundamentals are actually going to remain the same. So here, assume that so whenever we consider discrete features, we know that so for example, your features are actually again as a table, where say for example, suppose you have a say for example you have a the say gender of person, a customer, and maybe for example their maybe say dress size, suppose it's a large, small, extra large, medium, that's that kind of information. Suppose again that's a discrete one. Maybe gender is also going to be a discrete one, and maybe there suppose there is a attribute, so whether they are a student or not, so that is again a discrete one. So we'll have a yes or no answer. So assume that we are having a data set defined with a set of discrete features around. And a very particular maybe case is actually maybe this discrete actually variables actually say features takes only binary values. So that is a special case. That means they will take either 1 or 0. That means yes or no cases. So for example, you are asking so you are having a survey type of data collection where you are having a few questions. And so where you'll have the answers coming as 1 or 0 or yes or no, whatever it is. So that means all your features are assumed that is going to be binary type. So there are a lot of circumstances or problems where we will encounter with such maybe binary features. So that means assume that we have the variable x, okay, components of the feature vector x, okay, they are going to be binary or can be integer valued. Binary is actually a special case of integers, okay. So and x can take actually only, maybe assume that we have a set of values. So for example, only there are allowed set of values, we don't have any value defined in between, okay, those two different values. So for example, if you define dress sizes, for example, large and medium, okay, there is no size or anything defined in between large and medium, okay. So that means if it is medium, then after next you have only large, that's all, okay. There is no intermediate value. So that's why we have only a predefined m values, okay. So in that case, we have already seen the probabilities, how it will look like in Bayes formula. That is probability of w by given x is actually this equation, okay. And we have seen this equation maybe earlier, okay. So that is already the Bayes formula, okay. And the condition, risk, and all those things we have already discussed. But here, instead of maybe the throughout the integral, okay, we consider only for which I maybe the minimum value of risk actually comes. So that is a argument function. So that means this is called an argument function. So that actually returns for which value of the argument, in this case high, okay, this minimum risk is actually minimum, okay. So that I value will be returned and maybe corresponding maybe alpha value or whatever it is, okay. So for which I, okay, this risk is actually minimum and that particular risk is actually returned. So that is actually maybe the idea of maybe when it comes to discrete features, especially say for example binary features, okay, whatever case. And again, there can be a situation, we assume that the features are actually independent. So that means we assume that independent binary features, okay, a specific case, okay. So where we are, so for example, you have 10 questions in a survey and we are assuming that all these 10 questions are independent, okay. So that means the 10 features that we consider in that particular survey type of data is going to have okay, you don't need to consider any maybe covariance or maybe or any other, okay, cases, because they are going to be statistically independent, okay. So it's a very specific case only, but it is not applicable in many real situations, okay. Especially for example, when you consider a medical problem, you cannot actually simply assume that they are statistically independent, okay, because one feature will be dependent on maybe many other features. So that all these are actually depending upon which problem, how you would like to maybe analyze the data. All these are actually depending upon, okay. So assume that we are having a case independent binary features in two category problem. So that means we are having only two probabilities, two classes w1 and w2. So assume that so that means we have the feature vector, okay, in the dimension where each xi is either 0 or 1 with the probability. Suppose we define two probabilities, small pa and small qi, where they are actually defined for xi is equal to 1. So assume that our interest is actually when xi is actually takes a value of 1. So that means the binary variable actually takes a value of 1, we are interested, okay, suppose. So in that case, so given w1, pa is actually when xi takes 1. So similarly we can say 1 minus pa you can define, and similarly 1 minus qi is also defined. So qi is actually nothing but when the xi takes a 1 when the class is actually w2. So correspondingly we can have a for 0 value also when categories are actually w1 and w2. So that is the two probabilities that we gain here, okay. Now as we assume there is a conditional independence, okay, then so the interesting thing is that here we have a set of maybe x1, okay, x2, x3. So all these are actually independent, okay. So then this particular probability of x given wi, okay, we can just write as a product of, okay, these probabilities, okay. So the product of maybe I is equal to 1 there. So the pi actually indicates product, I is equal to 1 to d dimensions. So that means for each in a given feature vector, okay, in a given feature vector, say x1, x2, xd. So you consider x1, okay, and whether it is 1 or 0. Similarly, you consider x2 as a 1 or 0, and correspondingly you have a pa and 1 minus pa. So that is a this particular probability represents. Okay, so that is actually for when a class W1, this is a probability. And similarly for class W2, what is going to be the probability for given x, a given feature vector is nothing but, okay, we replace the P with the Qi. Okay. And using these two, okay, we can actually define a likelihood ratio as we have already discussed. That is against a product and the PA by, okay, so just from these two equations, we will get an equation PA by QA the whole raised to xi into 1 minus PA by 1 minus QA the whole raised to 1 minus xi. Okay, so depending upon whether xi is actually 1 or 0, okay, so if it is 1, then PA will be kept here, okay, and otherwise it is going to be this particular value. If it is a 0, then 1 minus PA will be the probability value that we will maybe using here, okay. The other one will become 1, also like that, okay. We can define the likelihood ratio also, okay. So that means so now we have already found out a likelihood ratio, and then we can substitute that into our decision I mean decision surface, okay, discriminant function, okay, equation. So that will yield actually, say this is equation, our equation, okay, we have already discussed this one, and we substitute this here, okay, for the likelihood, so that the equation will remain it will be like this one, okay, when you take it when you apply the logarithm, okay. So it is be xi into log of natural logarithm of PA by QA into 1 minus xi into natural logarithm 1, because this is actually the probability values. So the others are actually maybe the features. So that is the equation that we will get for a maybe likelihood, okay. And I'm sorry, for the discriminant function, okay. And now we can say that we can write g of x in this case, okay, as a in this particular form, okay. So which is I is equal to 1 to d, okay, wi into xi plus w0 form, okay. That is something like our earlier equation for continuous variables. So here also we are writing something like that one, okay. And then we define, okay, what is wi, it is actually from the previous equation. And similarly, what is w0, okay. So what is a threshold or bias, okay, in this case. And maybe the decision rule that we can actually apply here is, for example, we say that g of x is greater than 0, we say that it is w1, okay, and w2 is actually when, say, for example, g of x less than or equal to 0 or less than 0, whatever is the case, okay. So if you are actually not considering g of x equal to 0, okay, any of the classes, okay, again there are interesting things, okay, because this whole value g of x can be have influenced by what is the prior probabilities, okay, whether prior probabilities are equal or prior probabilities are different. All this can have a, okay, impact on whether g of x will prefer, okay, w1 decision or w2 decision, okay. So that depends on maybe how these prior probabilities are actually, okay, the case. So that is the way how we can actually maybe look at the base decision theory when it comes to the discrete features, maybe so these values are actually PA into 1 minus PA. It is actually only due to maybe the binary nature that we have actually discussed, okay. So that is the case, maybe how the decision boundary can be for a discrete features. So that is a case, and I think with that our first module actually comes to okay, end, okay. So next class I think we will have a quiz, okay, for this portions for the entire maybe assignment, sorry, for the module 1, okay, portions. So I will upload the remaining slides also. So that is a case. So I think next Tuesday we will plan for the quiz. If there are any changes, then I will inform. Otherwise, you please prepare for the quiz on next Tuesday. Okay. So that is for the time being. So we will see next class. Thank you.